What's up with my quarantinis? All right. In my Minecraft podcast, my gaming podcast, about the second episode, I was brainstorming a couple of ideas of what I can do with this ring right here, turn it into something actually functional. And the thing I came to make is the Electro-Magneto sense. So basically, what if you could design some sort of system, put it in a ring that would allow you to put your hand over your wall and feel the electricity running through it, or when you turn on a light, you can feel that, or when you have a changing magnetic field, like when you go to Walmart and those security things, you can feel that, right? I think that would be super cool. But and get some sort of haptic feedback so that you can actually feel that. But you need to charge it, and that's what I'm going to be investigating in this video. How in the world am I going to make a charger for a ring like this, right? And the kind of charger, wireless charger, obviously, there's no way I'm plugging this into the wall, a ring into the wall. There's no way wireless charger. You set the thing on top and then it charges. But how do I tell the wireless charger when the device is done charging? Or when it's there to begin with? How do I tell it? Well, there's different protocols and stuff. Your phone uses it. Most wireless devices use it. That communicates with it. And one of these protocols is called the Qi protocol. And basically, it uses some fun and cool properties of inductors, coils, electrical coils, that allow it to transfer information along with the energy without actually having to change how much energy goes through. But before we can make it, we have to understand how it works. So, that's coming up in a second. Now, if you've done anything with wireless charging, you know that they usually have something to do with coils. Well, these coils are called inductors, and yes, they are the primary way that we transfer electricity wirelessly. And a coil in electricity and electronics, its component symbol looks like this. So whenever you see something like that, that's a coil or an inductor. And how do you transfer power wirelessly? Before we get into transferring signals and all that stuff, how do you just transfer power? Well, we're using a cool property of electrons. We know that an electron moving through a wire creates a magnetic field around it, and that's just a property of electrons. So if we can get an alternating current of electrons, and the current is basically, you could think of it almost as the count of electrons, right? That's supposed to be a wave. Whoop, 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 whoop. That's a wave. AC current moving through this, it will create a magnetic field around it, all around it, that permeates throughout space, right? And these magnetic fields contain energy. But if we get another inductor or coil and put it next to it in close proximity to this one, some of the energy that is turned into this magnetic field around it will jump into the secondary and create an alternating current in the second wire. So all you need to make a basic wireless charger is have an alternating currents, have something going on and off, and then have a coil, and then put another coil next to it, and then you will be able to get current in the secondary wire. So that's super duper simple, right? Super duper simple. But how do we start communicating with it without having to change the voltage coming in? If I put my phone on my wireless charger, I don't want the wireless charger to start charging nothing. I don't want it to be on when nothing is there. And when my phone is done charging, I don't want it to keep trying to send it energy. I need a way to make it communicate. So, the way these devices do that is through this equation right here. And another thing that also uses this equation is near field communication. The thing on your phone, you could put two phones next to each other and it sends data. Near field communication. And this equation right here basically describes everything that it does. And yes, this equation describes an inductor. So a coil. And basically what this means is that the voltage across this coil is equal to the inductance, how well it can make magnetic fields, and that's measured in henries, times the derivative of current over time, or just how is the current changing throughout this coil. So voltage is basically telling you how much available energy is between here and here. How much energy do the electrons moving through here have? Right? That is what voltage means. This means how well it can make it in, how well it can transfer some of that energy into a magnetic field, and this means how many electrons are going through it, basically, and how that number is changing. So let's just see what that means. So I put a LED right here just for an example, and because we're dealing with derivatives, and this is the thing we're going to be changing, we're going to have to make a graph over here. So let's put 1 amp, and current is measured in amps, and then time, and then 0, 0 for both. Let's put 1 amp into it, right? Well, 1 amp right there, right? 1 amp, 1 second, right? Boom. For all of time, we're putting in 1 amp here, right? So if we put this in, what does this tell us? Well, first we need to put in a value for this inductor. So let's say it's 1 Henry. And 1 Henry is actually kind of a lot, right? So we put in 1 Henry. And then we also put in 1 amp of current this way, going out this way. What happens? Well, what is the derivative of this straight horizontal line? Well, it's looking at how it changes throughout time, right? But this line isn't changing. Its slope is 0, meaning its derivative is 0, meaning this is 0. So 0 times 1 Henry equals 0 volts. So we can conclude that if we put a constant 1 amp through this inductor, there will be 0 potential energy here. So this LED will not turn on. Okay. Let's put in 10 amps. What happens then? Same exact thing. It's not changing throughout time, so this LED does not turn on. But if we were to do something like, I don't know, let's change this. We'll put 10 and put 5. Let's say we do something like this, right? Every single second, it changes by 1 amp. So at 5 seconds, it's at 5 amps. At 10 seconds, it's at 10 amps. That means our slope is 1. Our slope is now 1, meaning the derivative of this function is 1. Meaning 1 times 1 Henry equals 1 volt. We will get 1 volt across here. This LED shines kind of bright. What if we made this even faster? What if 10, 20? What if every single second it went up by 2 amps, right? At 5 seconds it's 10 amps. At 10 seconds it's 20 amps, right? That means our slope is now 2. The derivative is 2, so 2 times 1 is 2. The voltage across this inductor is now 2. So if you see what's happening, the inductor cares about what happened before, right? It sees how the current is changing throughout, and then that somehow translates into a voltage across this LED right here. So, for example, if you were to get a battery and put it across an inductor, right? In the moment when it goes from 0 current, because when it's not connected, there's 0 current, and then as soon as we put it on, we should see a flash because the current would have changed, right? So we will see a flash from the LED. But if we keep it there, the LED will flash and then turn back off, and then there would just be tons of current running through it, but no voltage across here, so this LED would not turn on. And because there's a lot of current moving through it, because the resistance would be so low, it would look like a normal wire. So this thing will begin to heat up very much. So that's cool. Why do I care? And what does this have to do with near field communication? Well, actually everything. Now, in order to investigate how we can communicate data using this formula and these concepts, we have to understand why this even happens. So as I said before, if you get a coil, let's make another one. If you get a coil and run current through it, run electrons through it, in the nature of electrons, it makes a magnetic field around it. So if we put in 1 amp, meaning 1 coulomb of electrons per second, it's basically a count how many electrons are moving through it. That's what current means. You can think of it as water current, right? If I put 1 amp of electricity in, there will be a magnetic field around it that is proportional to that 1 amp. Okay? And as we said before, this magnetic field contains energy, and we can use that energy for wireless charging. That makes sense. But if we were to put in 0 amps, this should also be pretty obvious. 0 amps, there should be no magnetic field around it if they're proportional, right? So 0 current going in, there's 0 current, there's 0 magnetic field. That makes perfect sense. Now, what happens when we change it? Since this thing is dealing with change, what happens if we were to change it? Make the same coil, and we go from 0 amps to 1 amps and then back to 0. So let's say this is 1 amp. And our time doesn't really matter in this particular example. So if we go from 0 amps, it's running through it. There's no magnetic field, nothing changes, everything is nice and dandy. This is good, so 0 amps coming in, the energy is not lost at all. So the voltage coming in is the same voltage that comes out. There's no difference. There's no potential difference. None of the energy is being used to make a magnetic field. But when we change it, when we change this to 1 suddenly, now there has to be a magnetic field around it proportional to the current coming in. So we will see a magnetic field get generated around it, right? But because it went from no magnetic field to a magnetic field, and we know that the magnetic field uses energy, some of the energy coming in will be used, so less energy will be coming out, right? So the voltage coming in will not be the same voltage that comes out in that instant because it has to make a magnetic field. So we will see there is more potential energy this way, right? Because none of it is used here. And less potential energy this way, right? The electrons, because we're dealing with electrons, it's negative. More electrical potential energy, more negative here, less electrical potential energy here, positive. So relative to this is more positive. We have now established the voltage. But if we continuously put in this 1 amp, we don't need to use any more energy to make this magnetic field around it. We don't need any more energy. It's already there. So because we're not using any more energy to maintain this magnetic field, these go away. It's not using any more energy. It already has a magnetic field there. So the voltage disappears in these plateaus. Okay, so we have 1 amp coming in, and then we have a magnetic field, right, at this plateau. What happens when we drop back down? Well, turn this to 0, right? There's still this magnetic field here, right? Excuse me. There's still this magnetic field here, but we have to make this magnetic field proportional to this. So this magnetic field will collapse into itself. And what happens there? This magnetic field, because it contains energy, begins to give potential energy back to the electrons. So it gives the electrons here an extra push, right? It pushes more electrons. And because it pushes more electrons this way, we develop a second voltage when it changes, right? We develop a second voltage on the changes. But if you notice from the first example, when this went up, this one had greater negative potential energy, and this one had less. But when it's going down, it reversed. When the slope is positive, the voltage is positive. But when the slope is negative, the derivative is negative, meaning the voltage actually flips. So when it changes, electricity will be able to flow because this is a diode, a light emitting diode. And one way, when you connect it, it may turn on, and then when you disconnect it, it'll turn off. But if you flip flip the LED, when you connect it, it won't turn on. But when you disconnect it, it will turn on. So if you put two LEDs, let's just put another one right here, in reverse polarity, like that. When you connect this circuit up to a battery, boom, the current is flowing through it. We have this spike. Electricity will flow, right? The electricity will flow through one LED. If you disconnect it, this LED will turn off, and then this LED will flick on. That's what this shows. And the reason this happened is because of the magnetic field that this inductor induces, that it makes. This is where all the wonky this formula even comes from. It's because this magnetic field around it is collapsing and it's being maintained and everything. That is why the voltage comes up. So, what if we were to, I don't know, while it's changing. So, let's say we have a graph that looks like this. It's constantly turning on and off, square waves, just to keep it simple. Turning on and off, on and off, on and off very, very fast. We know these LEDs will be flicking on and off because it's constantly changing. These LEDs will be turning on and off, right? Due to the magnetic field having to be created and then collapsing on itself. That will create the potential voltage between it because some of that energy is either used or there's excess energy. So it will be turning on and off. Boom, 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 boom. What if we were to go in and get something and steal a bit of this magnetic field? If we were to take it so that it's not able to collapse back into itself. It's still flicking, but what if we could take some of that magnetic field? What would happen then? Well, we would see the potential energy drop. The voltage across this inductor would actually be negated. The effect, this thing stops working because the magnetic field that makes it act this way, we're taking it away. So we would see, if we were to somehow take it, the more magnetic field lines or whatever that we're taking from this oscillating, from this coil, from this inductor, the more magnetic fields we take, we will see the voltage across this, the average voltage across this actually drop. We would see it drop. And that's how we can send basic data without actually having to change the power being transmitted from this coil. We can change how much current is induced in the second coil. Or we can just, the more magnetic field lines we take, we will have an indicator that tells us how much we're taking. These LEDs just hooked up in parallel with it. So, and that's how it works. You can take a magnetic field. Take, don't take, don't take. And that will be a binary signal. And then you can communicate data without actually having to turn this thing off, right? So, in case you don't believe me, I'm going to show you a real life example. Okay, so just in case for the naysayers saying this is just math and math is useless, this is a real life example of everything that I just showed you on the board. I am going to connect this coil that I spun by hand and short it across this socket, which is running 12 volts. And I'm going to short it and in parallel, two LEDs that are in opposite polarity, like I showed on the board. So when I connect it, one LED should flash and the other LED should flash when I disconnect it. And this resistor right here is just so that I don't, there's a breaker inside the wall outlet and I don't want to draw so much current that it breaks that. So we're just going to turn on. Ooh, you can see the smoke coming off. So much current. When I connect it, and it's kind of hard to show because of the frame rate of this camera. So it's blinking and so fast that sometimes it doesn't catch it on camera. But if I do it really fast like this, you can see that it's not when I hold it, but it's when I disconnect does it actually turn on. So I'm going to stop that really quick. Others may say, how do you know it's just not something else? How do you know this just wire spooled around itself is even making a magnetic field? Well, we know that magnets make magnetic fields. And the thing about magnetic fields is that they can never actually intersect with each other. They emanate through coming out the South Pole and then into the North Pole, actually vice versa. And they can never actually crisscross each other. So what would happen is the magnetic fields emanating off of the ring will actually be pushed by the magnetic fields coming off of this magnet. So we should see the thing jump a little bit when I press the button. And that's clear as day. And when I don't have it connected, nothing. But when I connect it up to the magnet, there's a clear jump, right? So that is proof that there's even a magnetic. Okay, so what I've done now is that I got a little tired of pressing it on and off really fast, and I decided to hook up a thing called a timer 555, which generates that alternating current that I need. And but in this case, I actually use a MOSFET instead of a transistor. And what a transistor uses, it uses current to drive a larger current, which you can amplify with it. But because this is a field effect transistor, this uses voltage to drive a huge current. So that protects my timer 555 here from getting too hot because it's not drawing any current. So I have it set up, and then it amplifies the alternating signal. It's a few thousand hertz, and then it amplifies it, and it allows for wireless power transmission. As you can see here, these coils are inductively coupled, and they're not touching. But as I get closer, it gets brighter. Now that's cool. But this also has a bunch of cool properties. Number one, if I get something like paper, right, and then put it over it, the power is still allowed to go through. The power is still allowed to go through. Albeit less because it is being distanced from it, but it is able to go through various materials. However, it's not able to go through something like aluminum. Now, why doesn't it go through aluminum? It's because it's conductive. The alternating magnetic fields that's being emanated from it is actually being turned into a voltage by this conductor, and then it actually gets slightly hot. Yeah, it's getting hot right now. And that's basically the principle of induction heating. And what I'm going to do is hook up one of those detector LEDs so that we can actually see the magnetic field collapsing. So I set up the circuit, I changed the LED to red, right? And it's still inductively coupled. And then we also have an indicator LED. And the changes in the power when I use some of the electric field to turn into power for this LED, you'll see a tiny, tiny, tiny change in this. Can you see it? Hopefully it shows up on YouTube. But that's it. And as I'm changing this, I have both. I don't know if you can see it or not. But it changes as I draw power. And the more power I draw, the more this LED goes off. So I can prove that this actually takes some of the magnetic fields and turns it into magnetic field by simply placing above it, and then you can see how it changes. See that there? I'm taking some of the magnetic fields and converting it into thermal energy, and I can feel it slightly heating up. And then that energy is no longer able to collapse back and turn into a high voltage for this. So what I've done is lowered the frequency, and I put a magnet onto the coil. And as you can see and hear, it's making sound. Whoa. You hear that? This is how a speaker works. As you put a magnetic field through a coil, it causes it to rapidly move back and forth within another magnetic field due to the interactions of them. And this causes vibrations in the air. And as we add some sort of something that can also vibrate with it, it gets even louder. And as we increase the surface area, it should get even louder. So that's just a quick demo of how to make a speaker. Alright, so I saw the video was starting to get a little long, so I want to stop the video there. And I hope everything in this video made sense about the inductors, how it's the change in current that causes the magnetic field to actually change, and that change in magnetic field causes that potential voltage across that magnetic field. So if we're able to take some of that magnetic field, we can actually send signals to the coil and the charging device without actually having to send anything. Um, and that's what our wireless chargers use. And in the next video, I would like to start constructing this wireless charger with the near field communication, because that's basically what it is, with the near field communication, and making the charger for this ring. So that's probably going to involve a bit of programming, but that's going to be coming up in a few days. If you enjoyed the video, please like and subscribe.